First of all, thank you for joining us. Welcome to this presentation. And today's presenter is Mahya Roustaei. Mahya is a research associate at the University of Alberta. And today she will talk about application of the industrial computed tomography scanning in the characterization of permafrost and non-permafrost cores. And so I will start with a brief introduction about Mahya, and then we will listen to her and we will have a Q&A session at the end of the session. So Mahya, as I said, is a research associate at the UFA. She holds a PhD in geotechnical engineering from the Khaja Nasiruddin Tusi University of Technology in Iran. And she has 8 years of teaching and research experience on cold engineering topics at academic institutions in Iran. She joined the Railway Ground Hazard Research Program at the University of Alberta in December 2018 and started working on frost heave issues at railway tracks. She has successfully led complex projects developing numerical models to investigate the effect of climate change on the thermal regime of railway embankments. And she recently joined the Permafrost Archives Lab at the University of Alberta as a permafrost scientist to explore the non-destructive characterization of permafrost soils using industrial computerized tomography and multi-sensor coal logging system. Thank you again, Mahya, for accepting and agreeing to do the presentation and presenting your work here. And I think, yeah, we can start. To you.
Thank you, Zakia, for the introduction, and thank you for preparing or organizing this. Hello, everyone, and thanks for joining this talk. I'm going to have I think 20 minutes, not more than that, talk about the application of CT scanning in the characterization of permafrost and non-permafrost cores. And first of all, I should say that I was so lucky to join PAX Lab in early this year, and I should really appreciate Dwayne for giving me this opportunity and to join his team and have the chance of working with my awesome colleagues, Joel Pumpel and Jordan Harvey. And let's start talking about, just let me bring this here. Okay, so the non-destructive section of our lab mainly existed in these two parts. We have an industrial CT scanner, a Nikon one, and also a geotech multi-sensor core logging system. What you are listening today, the presentation and all the results are mainly focused on working with my experience with CT, but I also use the geotech as the verification source. So these two machines are mainly using for characterization of permafrost cores. We have the geotech with which is a multiple rapid non-destructive core logging system with a very high resolution images, as well as the gamma source, which will give us bulk density and we indirectly find the ice contents from it, and also the magnetic susceptibility, which gives us a very good idea of the organic content. But about the Nikon one, the CT scanner, we again use it for mainly collecting the cryostructure and the density and the ice content of our permafrost samples, which is just by locating sample between our gun and the detector, and after that finding the reconstructor model afterwards and start the image processing. We had a very great progress of finding a good housing for our samples to keep them cold during the whole scans. And just to give you an idea, that was the difference between the industrial and the medical CT scanners. This one has a very higher energy and also higher resolution, and do not require a dedicated room to operate, and also a very high maintenance cost. So this one cheaper to maintain and also operate. So my very first area project was looking at the unfrozen water content, which you know that has a significant effect on the thermal physical responses of soil. So I started digging into looking at some samples. I started working on with a clay sample, a kaolinite clay sample, which usually has a higher content of unfrozen water content. And it just used two sensors, thermistor and TDR, which give us the moisture contents, and start scanning the sample in different temperatures from -1 to -12, and looking to find if you can just find the unfrozen water content. And the resolution for these scans were 25 microns, and you can see the location of the moisture sensors and the thermistors, and the very first images of this falcon tube and the clay, the frozen clay soil inside. But the significant challenge of working with the, I think, CT images is working on the image processing part. We use Dragonfly as a very good scientific platform for image processing, and we found a good and very reliable automatic thresholding method or algorithm in this software, which is mainly working, which is called OTSU method, and it's mainly working with just, can you also hear the voice, or it's just me? Okay, if you can hear the voice, sorry, ignore it. So,
No.
okay, perfect. So it's working mainly with maximizing the interclass variance and just splitting your image into two intensity classes, higher intensity and lower intensity. And if you apply this algorithm to the top photo, you can see that your photo will be splitted to background with lower density material or pixels and foreground with the higher density one. So how this will work in our soil samples. So at the top, you can see that the cross-section of that falcon tube and the clay sample. And the very first split OTSU method gave us the sediments and ice. But we found that if we kept going an image processing with using OTSU method, we can find different parts of ice with different densities, or have the foreground and background even in the ice part. So I will keep it right now here. And before going more about the OTSU method, just take a look at the very small region of interest in this sample, and just take a look at the ice expansion during the different temperatures, which I just want to mention that the significant changes happens during lower temperatures or closer temperatures to -1. And when we are getting colder, the changes of ice or ice expansion will be low. Also, you can take a look at this video, which is showing the ice expansion, and the rate of the ice expansion is very fast at first slides, or at first part of this video, while at the second bar or towards the end, it will be slower. So the only point is that the significant changes, which comes from changing the unfrozen water content to ice, will happen in these temperatures. So let's again take a look at these two intervals, the background and foreground of ice. We found that while we are getting colder, or where the sample is getting colder, the background is not changing a lot, while the foreground part of the ice, which has higher density and closer density to water, is changing a lot. If we compare these changes with the moisture changes from TDR recordings, we can see that we easily can track 90% of the TDR changes, which is showing that although we cannot differentiate unfrozen water from ice in the images, but we can well track the transformation of unfrozen water to ice in our city images. So I think at this point, this was the most important, interesting results of this project. So we stopped there and we just jumped into the excess ice. And while you are watching this video from Brendan Olney, which is showing the significant impact of ice content on thawing rate as well as the amount of thaw settlement, I will bring some questions to start our next project, which was about the excess ice. We all know that excess ice is the amount of ice which exceeds the pore space of the soil. And why it's important, you can see why. Because it will bring a significant part of the thaw subsidence. And also, although it's so important, but there is very limited methods, great methods by now for finding the excess ice. And also there are low data quality and also variation of the data quantities. So it's very important to find out a more reliable method for finding the excess ice. The very common method of finding excess ice is just by grabbing this supernatant water that you can see in this video. But this method is not reproducible, it's not consistent, and it's not working well for organic materials. So our purpose is to find out a good non-destructive method for finding the best number of the excess ice. I used CT for the whole process of this project, but for verification of the results, I used the multi-sensor core logging system as a non-destructive method, but also used cubic method as the destructive one. Just give you a very quick information of this method is that we cut our cores to very small cubes in our cutting room, in our cold cutting room, and after that we found the bulk densities, supernatant water, and also the organic contents of the samples. So at the end, we had everything that we want from that cubes, and we compared the results with our CT results. In this project, we grabbed 5 different cores from 5 different soil types. We had an ice poor silty soil. We had a very good sandy silt, with a good layer of ice. We had a tall ice-rich peat, a transition core between silt and organic material, and the diamect core. And today I'm just showing the results of one of these core, which is our ice-rich core, ice-rich silt. So basically what we did, we splitted the cores into 2 parts, and we scanned one of them and we destroyed the other half. So for after scanning the half core, we did the image processing through all these blue cylinders that you can see in this image, which was our region of interest or ROIs, and we grabbed all the parameters that we are looking for from these ROIs. But what we did with the other half into 2 sets of cubes, and did the destructive cuboid method, as well as scanning the other set with higher resolution. So basically we had 2 different resolutions of our cores. One, whole core or half core with 65 micron resolution, and the other one, which we can scan it with 25 micron resolution. So again, I just want to go back to OTSU method, which previously used in our first project, but let's see what OTSU method is working here, or what's the results of OTSU method on this ice-rich silt core. We all know that in the permafrost core, we don't have just ice and sediments. We have sediment, we have ice-rich sediment, sediment-rich ice, and after that ice, and gradation between these 2. The OTSU method can break down these thresholds and give us a very good cutoff points from all these thresholds. So right now you can see that the very first image processing or very first OTSU method will just give us excess ice. But if we kept going, we can grab more ice, which is mainly the poor ice. And at the end, it gave us a very, very good number, very close. You can see in the next slide that these numbers or this amount of ice is very close to the volumetric ice contents of this sample. Again, in another spot of this sample, you can see that the very first image processing or split O2 method didn't grab pore ice, but the second or the fourth, sorry, the third or the fourth step gave us more of the pore ice. So mainly in CT scan, differentiation between different materials depends on their linear coefficients of the attenuation coefficients of their linear attenuation coefficients. So it means that if you have a multimodal histogram, each peak will present one material with different densities. But the challenging point will come whenever you have materials with very close densities that will all appear in one peak. At this point, the O2 method will give us a very good ability to differentiate these materials. So right now you're looking at our dimixed core, just a very small ROI of our dimixed core, and the results of the image processing using O2 method. And you can see that in the ice part, you have two peaks here, one representing ice and the other one sediments. And in the ice part, we have a lower density part, which is the visible ice, as well as a higher density part, which you can see it's showing mainly in the small pores. Again, in the soil or in the density, in the sediment part, we can also have different densities. So we can separate our sediments based on their densities. This image is also showing, again, the same method, the same image processing O2 method on our ice-rich silt core, which all these material just appeared in under one peak. And the left side of this peak is showing our excess ice and the pore ice, while the right side is showing different sediments with different densities. And again, in the transition core, we have the same. So it's interesting to take a look at all of them at one slide and see that the differences between different densities or different materials will be shown in the different histograms. So to me, it looks very good, and I think that we are doing very great in the image processing parts. But at this point, we should verify our result with something else or with some other results. So let's come to the results of cuboid method as a destructive method and the geotech as another non-destructive method and compare them to our CT results. I know that it's a very busy slide, but bear with me, I will just make it simpler for you. This is our ice-rich silt core, and this is just the ice part. I mean that's the darker means more ice. And you can see this beautiful ice lens here with a dark line here. So the first column of the results, it's showing the density. You can see that the black line is from geotech and the red line, which is from CT, are in good agreement. And we can compare them with the results of the cuboid method. I should definitely mention here that the resolution of the cuboid method were 2 centimeters, while the resolution of our geotech and CT image processing was 0.5 centimeters. So higher resolution will give us better density distribution. But if you can see some differences between these, between the destructive and non-destructive method, it's all the is the effect of resolution. And regarding the exercise, again, I want to start first from the red part is just showing the exercise. The cubes is showing the exercise of the cuboid method. The red line is showing the exercise from CT. And also the black, again, is showing, but not the exercise, the volumetric ice content. So we can see that we had a huge difference or a huge shift between the results in the ice layer part. And the main reason is that during the cubic method, we couldn't grab the ice layer, but in the geotech and in CT, we well tracked the ice layer with a very high ice content. So when we are trying to just push our O2 method to find more core ice and volumetric ice content, we found that in this core with the scanning, with the 65 micron resolution scan, we just had the success to find out a part of volumetric ice content, not the whole volumetric ice content, which right now is shown here by gray blocks or cubes. But we put another effort of scanning smaller parts or cube of these cores with higher resolution. And this black cubes is showing higher resolution. And the numbers regarding the excess ice or the volumetric ice contents are very close to the cuboid result. So it means that if we can go for higher resolution, we can grab almost all the pore ice and give the number of the volumetric ice content. We also had another column in our results which showing the organic content, which for this one, it's not a big or a significant effect on our results. At this stage, just a very quick comparison between the excess ice that we grabbed from our destructive method and the excess ice which we grabbed from our image processing of CT scans shows that we are in a good agreement, and the numbers is showing that the image processing is really worked well in terms of finding the image, finding the excess ice of our images. So now let us just have a quick talk about the resolution. So to find out the effective resolution, we scanned one cube in two different resolutions, 65 and 25 micron. And you are looking at the very small region of interest from these two cubes in the down part of the slide, working, showing how the image processing is working and grabbing the ice. So the first part is just the first split, and you can definitely see that how the 25 micron can give us more excess ice and more details. If I grab the numbers or the amount of this excess ice and bring it to this top right photo, you can see that these numbers from ice are very close to the excess ice content that we grabbed from cuboid method. So at this point, we found that both scans gave us a good estimation of the excess ice, and the difference between these two is showing the resolution effect. But what if we keep going on the image processing and try to grab more pore ice? So this is one of the, I think, interesting points of this project, that we found that putting more efforts on splitting the material and finding more ice, first of all, will let us to be very close at the end to the volumetric ice contents of the cube extracted from cuboid method. But it's also showing us that with some resolutions, let's say 65 micron for this silty sample, we can never reach the final volumetric ice contents with lower resolution. So the higher resolution will definitely works well. And also we can see that the amount of ice is decreasing exponentially, and it's showing the reliability of the O2 method for us. And at this point, we found that, okay, so the well-established non-destructive method, or we proved that a non-destructive method can be used for finding the excess ice content and volumetric ice content. But right now, what do we want to do with this data? What if somebody doesn't have access to these techniques? So what's the point of doing this? We found that if we can just find correlations between the physical properties of soils or our pores and the volumetric ice content and excess ice content, it will be a good approach for us to have the minimum data and go for finding the highest quality data to predict excess ice. So we started plotting excess ice contents versus volumetric ice contents from these two different methods, destructive one, and destructive one. And you can see that the numbers really looks good. So we kept going with the cuboid method to add more points to find the better correlation. Right now, you are looking at around 100 points from 5 different cores, and you can see that the relation between excess ice and volumetric ice content. At some point, we found that if we normalize our axis or our numbers to the soil density, we will have a better relationship. So you can just compare these two with each other. I'm not sure where is the relationship. Okay, it's not showing. Yeah. So at this point, we found that this is exactly the next step that we are going towards that, to find the correlation between the physical densities of soils and also the volumetric ice content and excess ice content. So this is the next step of this project. Next part is about the unfrozen samples. I brought this here because we had a great progress in doing the porosity analysis of some fiber reinforced clay soils, which can be of interest for any projects. I mean, the porosity analysis is a very significant tool for finding out the effect of lots of things: treatments, curing time, climate conditions, freeze-thaw cycles, and the microstructure of the samples. In this project, we used the same kaolinite clay, but this is the very raw image of our clay sample, and we were very lucky to find out a very good porosity or void space of this sample, as well as the fibers, which have not been shown in any studies that they found the orientation of the fibers or locations of the fibers. So it was a very promising result at this stage for us. And we kept going with applying different freeze-thaw cycles. And the first show or the very first results of the histograms show us that after the cycles, we have different peaks on the pore size or the porosity. So it's a sign of porosity changes. But how we can go deeper in these changes? The porosity analysis was the great tool to, I just did the porosity analysis on a small ROI because it was very easier to show how it's working. And also you can just, I don't want to go for the details of these figures, and I just want to let you know that in porosity analysis, you can just put your porosity in different orders and find out the distribution of that orders, the volume of that orders, even the surface of that porosity type, if it's a macropore, if it's a mesopore, if it's fissures, and find out the changes of that fissure in different samples, which here I did, and I found that the unreinforced sample has higher fissures after the freeze-thaw cycles. And this is a very quick video of our samples before and after the reinforcement, and also after freeze-thaw cycles. You will see the fissures in red, macropores in green, mesopores in blue, and fibers in orange. And you can see that the clay is dissipating from the samples, and the macropores is also dissipating, and the mesopores. And only at the end, we will have the fissures and fibers. And you can see the effect of freeze-thaw cycles on the reinforced sample, and also, sorry, on the unreinforced one, as well as the reinforced one. Again, sometimes the numbers will give us very good idea of what's going on instead of just visualization. So these are the numbers that I grabbed, and I found that, again, the fissures has a significant amount of pores after the cycles, which can definitely affect the strength of soil, the permeability, and other parameters of the soil. So this was the end of the my fiber project. And I just want to wrap up the presentation with 3 slides from our last scans of full pores, which were very interesting. and I think it's worth bringing them here. We recently scanned a geotechnical core from Peace River, and our first attempt was scanning the core completely sealed. The core has a layer of wax, it's a big layer of wax, and also a PVC that you can see in this picture, and this was the core. So we first scanned the core when it was completely sealed, and after that, we opened the core and again scanned the open one. So it was very interesting for us that we almost found the same structure and the same details of this core while we scanned it even completely sealed inside the PVC tube. You can see in this video that that's the scan of the cube. So this video, in this video, first the PVC tube is dissipating, and after that's the clay, the material. And after that, the only thing that will remain is the burrows and the structures and their distribution in the sample, which looks very interesting for us that we can just reach this much details even from sealed sample, and we can penetrate through this core. Yep. I should also mention that Jordan Harvey did a great job of preparing these videos, and also he provided me with another video from one of the Hope Bay mine cores, which is a clay core, a glacier sediment core, fairly ice rich. You can see the ice lenses, as well as a quick video that is showing also how this material is strongly impacted, or the edges are strongly impacted by the drilling technique, although it was an ultrasonic drilling technique, but it's, I think, the outer edges were towed, and you can easily see what's going on after the sample is drilled. And this is the last slide. And thank you so much, first of all, from PermafrostNet, which I'm a member, and also the PAX Lab, and my colleagues, Dwayne, Joel, and Jordan. And let me know if you have any questions.
Thank you so much, Mahya, for your presentation. It was a very impressive work. If anyone has a question, please just unmute and you can ask your question.
I have a couple of questions.
Yeah.
So thank you, Mahya. I think I didn't write it down, but the software you use is quite impressive. I'm going to have to take a look at it for those videos.
Yeah.
Okay, yeah, very, very cool. If you go back to slide 16, I believe, I just don't understand what the different steps you took to get to that, to the volumetric ice content that you were looking for.
Yeah, different steps is a different number of also method or splitting methods that we applied on the sample. So it means that at very first image processing step, we just grab the excess ice or the visible ice, while we are going further, we can grab more of the poor ice by just splitting different parts of our images.
Okay. Okay, thank you. And then my second question is, you mentioned foreground and background, and I am not familiar with those two terms, like earlier in the presentation.
Yeah, so if you can see the top one, this is the original one. And this is after applying the Otsu method, which just splitted your picture or your image to two different intensities. The lower ones, or the lower density ones, will be your background, while the higher one will be your foreground.
Okay. Okay, great. Thank you very much.
No worries.
Mahya, following the Tabata question, again on slide 16, I have a question.
Yep.
So my question is, how did you get like the volumetric ice content? I mean, how the result of CT scan are converted to volumetric ice content?
In Dragonfly, whenever you split something as a new region of interest, you can have all the details of that region of interest. You can have the volume of that region of interest. You can have what else? If you are looking at the surface of that, you can find the surface. So all of them is just the options of the software, which will give you the volume of that whole of that interval in your whole sample.
Mm-hmm. Okay, and you compared like what you get from this with the like the cuboid method. That,
yes.
So in borehole logs, so maybe I can start with this question: how these kind of microstructural analysis can be upscaled to a scale that can be more applicable. By applicable, I mean, let's say, how we can upscale these results for a borehole, not for a sample.
We were talking about this a while ago with Wayne. That's it would be perfect if we can just go for scanning lots of cores. I mean, just to increase the number of the scans that we can have, and to maybe make a database of the visual. We cannot talk about the 3D one. We can just talk about the 2D one if we want to compare it with what we are grabbing from the boreholes, because the boreholes will be, everything will be done at site. So everything will be 2D just by visualization of the core. So we were thinking about if we can just add a big database of the different materials, the different cryostructures, and different ice contents. So it might be just a good way of upscaling these results. But for now, right now, no, we don't have any option for that. But definitely, we should go for scanning lots of cores.
Mm-hmm. Yeah, I think that's a good idea actually. Yeah. Like to make that database and then have these like representative samples of like different conditions.
Same as the standards or the common things that they are using right now while they are logging the core, and just the visual inspection of the core and giving the number of exercise. It might be also useful. Yeah.
And in one of the slides, I just it was an observation, like I think maybe slide 16 or maybe like 18. I'm not sure. Yeah, like these graphs. Yeah, here. Yeah, exactly. Like we have here for the peat samples, we have volumetric ice content of 100%, but this volumetric ice content is like when like the corresponding excess ice content has a larger range.
Yeah.
So
you mean why the numbers are? Yeah.
Yeah. So the question is like, for me, volumetric ice content of 100 means like we have an ice sample, and the excess ice has to be 100%.
Yeah.
In this condition, yeah.
First of all, the issue with the organic contents is that they will hold the water. So I mean, it's not as easy as just taking out the ice layer or ice part from a silty sand. But when you are looking at the organic material, and also the density are very close to ice. So it's mainly a mixture, a good mixture, homogenized mixture of ice and organic material. And these ones has very, very high gravimetric moisture content, maybe around 1,000, something like that. So the moisture content is very high. And as you can say yes, in some ROIs, we had 80% of ice and just 20% of material.
Mm-hmm.
Yeah.
Okay, I could see like you were getting better correlation when you were dividing these like numbers by
yes.
the
Yes,
like
normalizing them.
Yeah.
I have a question, Nigel here. Thanks very much for the presentation. Very good. I was interested in the sample which was covered with wax, and you didn't have a open it up and look at the sample. Can you see what the gradation of that material is? Is it a silty sand or a sandy silt? Are you able to discern what the material type is?
I believe, but probably I will ask Jordan if he is still. Yep, Jordan is still here, and is our resolution enough to find the grain size of this, or?
No, not for this core. The resolution wouldn't be fine enough, but it was a shale, so it was very fine grained.
Yeah, okay. Yeah, thank you very much.
You're welcome.
And yeah, we can end the session. Thank you so much, Mahya. Again, that was a great presentation, great work. And like, I know that you have done this work in 1 year, which is impressive for me. Yeah. And thank you again for accepting to do the presentation and sharing your result with us here.
Thanks for just giving me this opportunity. And it was a very good work, promising results, because it was not just by me. So I had very good support from Joel, Jordan, and Dwayne to just finish all of this in a year.
Yeah. So thank you everyone for joining, and have a good day. Yeah.
Thank you.